Okay, so right now we're going to solve using Euler method this equation. Y prime is equal to 4 e to the 0.8t minus 0.5 y. So let's save this as, let's say, uh, this one. So this is ODE. Okay. So the solution would be, so of course we want to set up first our initial values. So for example, we have uh, your time, which is from 0 to 2. Okay, and let's say the step size is h, and that is equal to 1. So this is h to 2. Kita ba?
Yes, sir.
Okay. And then initial value ni I, so that's yi, a y naught would be equal to 2. Okay. So let's try to implement this. So 4. So what's the length of our time? So that's length of time, because that is what we need to know how to uh, do the increments. Okay, because we need it for the I. So I would be equal to 1 to the length of time minus 1. We cannot go up to the end kasi kailangan natin yung the following term niya. Okay? Let's put an end here. And then, what we can do here is we compute for y, which is equal to y naught plus our function, which is a function of y and t. Okay. So how do we do that? So we define our function. Okay, so our function dy dt is what? Is a function of y and t. And that is equal to 4 times exp of 0.8 times t minus 0.5 times t. Sorry, times y. Okay, so this is dy dt, which is a function of y naught. This is y naught times time. So what is our time here? Our time here would be the element of your time here. Okay. So let's try to scatter first our y and t. For that, let's try to plot just for comparison purposes. Let's plot the analytical solution. Okay, we can copy the whole thing here. This is your y a, which is a for analytical. And then let's in space, let's say 0 to 4 with 100 points. And then let's plot figure handle and plot t, y. Okay, so before we proceed here, let's put a breakpoint here, save, and let's run at the path. Okay, so there's an error. Okay, so there should be a multiplication sign. Mm-hmm. Okay. So we're waiting to plot. Okay. So this is the plot. Okay. So quick debugging. Let's put it here. And let's turn on the code to plot this, guys. Okay. So let's start here. Save. Run. And then step. Okay. So y is 5. So baliktad to. So this should be t, y. Save. But here we're solving the value of y after the initial condition. Okay. So that means
So wala po bang times h yung dy dt dun sa y?
out. Okay, tama. Dapat may times h ito. So, but actually, it will not matter right now because h is 1, but it should have a h there. Tama. So let's run again. Let's close this step. So that is where your y should be. But as I mentioned before, the time here, this is plotted at time I plus 1. So this should be a time plus h. And then we have to update the value of y naught for every iteration. So that means the new y naught will be the old y. Yeah, this should work. Okay. So nakita nyo? Hindi kita yung black and field. Let's run. Tama ba? Bakit hanggang dalawa lang? So 0, 1. So ilan yung time natin?
Hanggang 4 po.
Hanggang 4 dapat yung time, di ba? Ba't hanggang 2 lang? Kasi ano yung length time natin? Okay. So just to verify, so we can check the okay. Time is 0, 1, 2 lang. So dapat hanggang 4 to. Okay, good. See. So let's run. Okay, here. This is your solution to your differential equation. Okay. So what we can do is put all these solutions to one single variable, to one single array, so that we can plot it together later. Okay, so let me skip this first. Okay. So what we can do is we can define a y solution vector, which is an empty vector. And then at the end, once we solve this, we will put the value of y to this y sol. So we're going to build this array. So y sol is now equal to y sol y. And then our t sol will be t sol with a value of t plus h. Okay, so this is t sol. Nakita nyo ba yung ginawa ko dito? Nakita nyo ba?
Ano pong ginagawa?
Okay, so at the start, before I increment, I define these two variables. Okay, so let me go up to this point. Okay, let me close all. So let's run. Okay, so let's identify t sol and y sol. Okay, and then I'm going to view. Okay, so this is t sol and y sol. Okay, so from our previous example, so your plots should be at 1, 2, 3, and 4, diba? So if we're going to increment this, so the value of t here would be 0. Okay, and the value of y would be 5. Okay, so 0 and 5. So this number 5 will be added to y sol. And then the next, the time assigned for y would be t plus h will be placed to t sol. Okay, so if we're going to look at these two variables, so when I step it, so may 5 dito. And then t sol will be 1. Okay, and then we continue until the end. So this is now your solution. So that at the end, we can now plot t sol and y sol. Let's say black circle, and then base color is black. Okay, so save again. So let's try to run. No face color. Color lang pala. Sorry. Sorry. Ang tawag dito, ang tama dito. Marker color. Run. Wala pa rin. So, sige. So, tanggalin na natin to. Okay, so run. This is your solution. Kita niya? Okay, this saves time. Kasi for every time you plot it, every increment would take a lot of time. So might as well collect everything first, and then you plot it later. But you will notice that there's a warning here. Okay, so y sol appears to change size in every loop. So considering pre-allocating for speed. So what do you mean by pre-allocation? So when you start these two variables, before you increment, you don't know the length. Okay, you assume na you don't know how long this will end up. That's the assumption. But we know that based on our time variable, okay, because time, the length of time, so if we're going to calculate the length of time, the length of time is 5. Okay, and you know that by Euler, by the Euler formula or Euler method, the resulting derivative or the resulting solution would be n minus 5. The length would be n minus 5, n minus 1. So that's 4. So in reality, you already know what to expect with y sol as well as t sol. So what we can do here is instead of defining this as empty array at the start, what we can do is we pre-allocate a space. Okay, so you already know that this y sol has a length of 5. So you can make an array that 4, and then you can make an array with the that will represent y sol with an one-dimensional array with 4 elements. So there are several ways to do that. So for example, what we can do is we can use zeros. So zeros is a function that creates a an array of m by n dimensions with value 0. So we know that this is a 1 row by 4 elements, diba? So how do you know the element? So let's type in n minus 1. But we have to define n here, which is the length of time. Nakuha ba ko? And we can also do the same here. Okay, so let's save. So let's stop at this point. So let's run. Up. So this should be zeros, walang e. Okay, so you will notice here that I made two vectors, t sol and y sol, with 4 elements already. So what we will do in this iteration is we're going to replace these values with our actual values. So instead of this one, this is building array, what we can do is we assign the position of I sol I. We put the value of our solution y to each increment of I, each increment of y sol together with. So that's pre-allocation. So you can see that there is no more warning. So this is an equally valid result. Okay. So let's try to hit debug and then run again. Okay. So this is faster, especially when the time difference right now is insignificant because we're looking at 4 elements only. But if you're working for, let's say, 10,000 points, okay, this may take time. Okay, so what happens here is that you are pre-allocating a space from your memory that is dedicated to your solutions. Do I make sense? So yun yung nangyari
Yes.
dito. Okay, that's pre-allocation. Okay, so let's try to clean this code by setting up our initial value for ti. So ti, which is 0, tf should be 4, and then let's say h would be 1. What else? Yeah, okay. So that this t will be from ti to tf, and then this is the numerical, the Euler method. So h has already been defined. Time I, sige, ito, yan na rin natin dito. Why not? Okay, pwede natin itong delete. Time would be from ti to tf with increments of h, then n. And then we define this function here. Then y sol with n. So this would be n minus 1. And yeah, that's cleaner. Okay, let's run. Okay, that's a solution. So we can extend this to, let's say, 5. Okay, and then we can decrease the h to, let's say, 0.5. Sorry, let's run. You see, let's try to remove the close. So let's run. And then increase further your h to 0.21. So you will notice that as you increase your h, the solution to your differential equation approaches your value. Now let's look at how this performs by plotting the difference. So let's plot the difference. Okay, so first let's define the difference. Okay, so let's say time. Our time would be this one. So let's copy this here. But instead of using t here, let's use time. Okay. I'm going to then I'm going to plot time with YA. And then this time, let's use square that is red. Okay, let's see what happens. Okay, so the red one are the true solution. The black one would be the analytical solution, the numerical solution. Okay, just to be clear, let's make this one. Okay, so you can see that. Okay. Now, as you will notice here that the difference between the analytical solution and the numerical solution, as you will notice here, increases as you go away from your initial condition. Okay, so how do we do that? So we can do that by uh, uh, taking the difference in y, which is the YA minus Y sol. Then let's plot it again. It's time, then dy. That's the difference between the y's. And let's use a simple line. Let's run. Okay, there's an error for dy. Why? Because YA is supposed to be 6 elements, but Y sol is only 5 elements. As you notice here, merong analytical solution here, but there is no solution to the numerical solution. Okay, so what we can do is we can get the only this point up to this point only. So that's Y2 up to the end. And then let's run again. And then continue. So RA out of bounds. So what's YA2? Sorry, YA2 to the end. Sorry, it should be 2 to end. Save, then run. Must be of the same length, so that means your time should be from 2 to end as well. Okay, or you can use T-sol here. Madali naman T-sol. Run. Okay, so this is the difference. Am I making sense?
Yes, sir.
Okay, we can place additional lines connecting the dots. So let's run again. Okay. So even if we increase your h to, let's say, 0.2 or 0.25. You can see that as you go away from your initial condition, your approximation error or your error in your approximation increases as you go away. So this is the same thing why, for example, when typhoon track forecasts are determined, because when you forecast, okay, you're only dependent on what is the condition at the present. So when you approximate what will happen farther away from what is it now, the error tends to get bigger. So that's this solution means here.